Hello friends, welcome to engineering tutorial. Today we are going to study about another transducer which is a strain gauge. It is basically a resistive transducer. So it's based on resistance or change in resistance or property of resistance. So let's get started. So what is a strain gauge? Now, a strain gauge is basically a primary transducer. It's a primary transducer. So, it's a primary transducer. It means that it converts physical quantity which is under measurement into mechanical signal. A mechanical motion or displacement, any type of mechanical signal. So, it is a primary transducer which is basically used for measurement of strain, stress, displacement, force and pressure. These physical quantities are measured with the help of a strain gauge, and as it is a primary transducer, in order to convert the output into suitable voltage or current signal, we have to use a secondary transducer or a signal conditioning circuit. So, what is the operating principle of a strain gauge? Strain gauge operates on the principle of piezoresistive effect. As I said, it is based on change in resistance. Its property is based on resistance, which is called as the piezoresistive effect. Now, what is the piezoresistive effect? Now, we know that the resistance of any material is given by the formula R is equal to rho into L by A. We know R is the resistance, rho is the resistivity of the material, L is the length of the material, and A is the cross-sectional area of the material. Now, here there are three important things to take note of. Resistance is directly proportional to resistivity, resistance is directly proportional to length, and resistance is inversely proportional to cross-sectional area. So, it means that if resistivity increases, resistance will increase, and if resistivity decreases, resistance will decrease. Similarly, if length increases, resistance will increase, and if it decreases, it will decrease. But resistance is inversely proportional to area. So, if there is an increase in area, there will be a decrease in resistance, and if there will be a decrease in area, there will be an increase in resistance. These are the three things which are exploited in the piezoresistive effect to construct a strain gauge and to measure physical quantities such as force, pressure, strain, stress, etc. So, as I said, there are three possible ways in which there can be a change in the resistance of the material. There will be a change in length, or a change in cross-sectional area, or change in resistivity. In this, in the case of strain gauge, change in resistivity does not play any part. Only the change in length and change in cross-sectional area is considered. Change in resistivity takes no part in the strain gauge. So, first let us consider change in length. As I said, the resistance of a material is directly proportional to the length of the material. So, as the length increases, R increases, it increases and vice versa. Means if length increases, R increases, and if L decreases, R decreases. So, here we have tried to put it in terms of a mathematical formula. So, let us say that the initial resistance is R and the length of the material which is subjected to compression or expansion is changed by a factor del L. So, if there will be an increase in the length which is given by the positive sign, there will be an increase in resistance by a factor del R. If there will be a decrease in the length minus del L, there will be a decrease in the resistance by a factor minus del R. A is constant. Here there is only change in length which is considered. Similarly, let us then consider change in cross-sectional area. Resistance of a material is inversely proportional to cross-sectional area. So, if cross-sectional area increases, R decreases, and if area decreases, R increases. Here, the resistance, let us say the initial resistance of the material is R, which is going to be subjected to any force or pressure leading to compression or expansion, and due to that there will be a change in the cross-sectional area. So, an increase in the cross-sectional area denoted by the positive sign here will lead to a decrease in the resistance denoted by the minus sign by a factor del R. And if there will be a decrease in the cross-sectional area due to stretching or expansion of the material by a factor del A, there will be a corresponding increase in resistance by del R, which is denoted by positive sign. Now, there are two important things here. As length is directly proportional to R, the notation plus minus sign, they are the same in both the cases. But here in cross-sectional area it is opposite. Here it is minus plus, here it is plus minus, because here resistance is inversely proportional to cross-sectional area. So, always make note of this. Do not ever write plus minus in this case of cross-sectional area, it will be wrong. So, resistance is directly proportional to length and inversely proportional to cross-sectional area. Let us try to understand it. Suppose, let us say there is a material, this large cylinder. It is a material, it has initial length L and diameter D. Suppose it is subjected to an expansion force, it is stretched because of this applied force, it is stretched. So, it undergoes expansion. Because of expansion, there is an increase in the length of the material and the length increases by a factor del L. But because of expansion, the diameter of the cylinder or the material, it decreases by a factor del D. As a result of that, the cross-sectional area also gets reduced. Now, because of this applied force and expansion, there is an increase in the length. So, there will be an increase in resistance, because resistance is directly proportional to length of the material. But as the cross-sectional area gets reduced, there will be a increase in the resistance as well, because cross-sectional area is inversely proportional to resistance. So, in both the cases there will be increase in resistance, as both the factors, that is increase in length and decrease in cross-sectional area, support an increase in resistance. Okay. So, in both the cases there will be an increase in resistance. So, normally the strain gauge comes in this configuration. It consists of a number of turns of wires which are wound over two platforms. Out of these two platforms, one of the platform is fixed and the other one is movable. Now, the force or the pressure or the displacement or motion which has to be measured is generally applied on the movable platform, so that whenever there is a force which is applied, there will be compression or expansion in these wires. Now, because of compression or expansion, there will be a change in the resistance in these wires, and this change in resistance is converted into suitable voltage or current signal with the help of a signal conditioning circuit, which is basically a Wheatstone bridge. So, here we use a Wheatstone bridge for signal conditioning, and the strain gauge is used in one of the arms of the Wheatstone bridge, and the voltage output is taken across these two ends, the opposite ends across which the DC supply voltage is given. So, the opposite ends, across the opposite ends, the output voltage is taken, it is amplified and is given to a digital readout or a pointer scale indicator. So, basically Wheatstone bridge is used for signal conditioning. So, the resistance of the strain gauge, it forms one of the arms of the Wheatstone bridge. Now, there are two important parameters which are associated with the piezoresistive effect or the strain gauge. Those two parameters are the Poisson's ratio and the gauge factor. These two parameters are very important when it comes to strain gauge or the efficiency of a strain gauge. Now, what is Poisson's ratio? Now, Poisson's ratio is generally defined as the ratio between the per unit change in diameter of the material divided by the per unit change in length. It is also written as the ratio between the lateral strain and the longitudinal strain, which is given by del D by D by del L by L. This is called as, this expression is for Poisson's ratio and is generally negative, the negative sign. Another factor which is another parameter which is associated with strain gauge is the gauge factor. Now, what is gauge factor? It is defined as the ratio between the per unit change in resistance of the material divided by the per unit change in length, which is expressed mathematically as del R by R by del L by L. This is gauge factor. Now, both Poisson's ratio and gauge factor are related with each other. So, the relationship between Poisson's ratio and gauge factor can be written as 1 plus, so the gauge factor is equal to 1 plus twice of the Poisson's ratio plus ratio between per unit change in resistivity by per unit change in length. So, as I said, the change in resistivity is generally ignored in case of strain gauge. It is not considered. The change in resistivity is not considered. So, you can just write down that gauge factor is equal to 1 plus 2 into Poisson's ratio, 1 plus twice of the Poisson's ratio. This is gauge factor. This is the relationship between Poisson's ratio and gauge factor. Now, some of the materials which are used for construction or the building strain gauges are listed below. They have the resistivity and gauge factor values are also given. You can note them down if you want. So, basically platinum is used, platinum and nickel is basically used for construction of strain gauges along with constantine nichrome, and other semiconductor strain gauges are also available. Then there are bonded and unbonded strain gauges which are also, there are many materials used, but these are basic 4 materials which are generally used for strain gauges. So, the resistivity and gauge factor values are given, you can note them down if you want. So, here we have studied the basic principle of operation of strain gauges. So, as I said, there will be either a compression or expansion of the material. Now, if there would have been compression here, there will be compression of the material, there would have been an increase in the diameter leading to an increase in the cross sectional area and a decrease in the length. In that case, there would have been a decrease in the resistance, as both decrease in length and increase in cross sectional area support a decrease in resistance. So, these are the normal things which happen in a strain gauge. There will be either compression or expansion. In case of expansion, there will be an increase in resistance. In case of compression, there will be a decrease in resistance. Why? Because the resistance is directly related with length and inversely related with cross sectional area, and the relation of resistance with resistivity is generally ignored in case of strain gauge. So here we have studied the basic principle of operation of strain gauge. So please subscribe my channel Engineering Tutorial for more such videos related to electrical and electronics engineering. Have a great day. Thank you very much.